Hi viewers, this is Dr. Gunamani Jana and you are watching video with me on data structures, and today's data structure class will be covering the AVL tree. This is the outline. What is the AVL tree and why we go for this AVL tree? The different rotations will be applying there, and the AVL tree insertion, deletion, some key points and references. So we know about the binary tree and binary search tree. For binary tree, as I told you that in the previous video, that a parent can have a maximum two children, right? Except the leap, whatever the thing there. So it should not exceed the two child. Clear? This is the thing. So it can have 0, it can have 1, or it can have maximum 2. Then what is the binary search tree? In the binary search tree, so we see that what are the key means, what are the circular things we are writing here. Say it is a node. The root node, the value is, you can see it here, it is key is 10. Okay, so this is the root node and this is the key, and this is another subtree where this is the, I think this is the key value is equal to 14, and this is, I call it a subtree. Now while you are going for this binary search tree, all this key to the left side of this root should be less than that one, and all this key value to the right side of this root node should be greater than this 10. Clear? That means you see here it is 4 is less than 10, here it is 14 is greater than 10, and here also 19 is greater than 14, 19 greater than 10, and it is 11 is greater than 10 but less than 14. So in this way, while you are going for this binary search tree, there should be must be some sorting orders, right? So this is strictly how to follow, that the left hand side would be lesser key value and the right hand side would be larger key value. Then we have gone for the balanced binary search tree, or BBST, balanced binary search tree. So we have number of balanced binary search tree. One is the AVL tree, second one is the red black tree. Okay, so this AVL tree, so this is a special type of tree that has several properties. Let us summarize the properties. First one, it must be a binary search tree, that is the first one, and it must be balanced in nature. First thing is that it must be a BST. BST means binary search tree, so it has to strictly follow the left side key values must be less than the root, and the right side must be greater than that one. Then it will be self balancing. That part we will discuss. What is the self balancing? So there will be using one balance factor or balancing factor, whatever you say, that will check it. Okay, for each and every subtree we will check the balance or balance factor. Then it is not perfectly balanced. What is that perfectly balanced? Let us have the discussion about these things. If all the internal nodes have two children and all the leaf nodes are the same level, then we say it is a perfectly. Okay, but here you see all the internal nodes, you see all the internal nodes have two children, but okay, this is internal node. Okay, it has two children. Clear? This is the all the thing it is there. Then second thing is that all the leaf nodes are at the same level, but you see all the leaf node, this is level 0 and this is level 1, so all the leaf nodes are not at the same level here. Okay, so all the internal nodes have two children and all leaf nodes are at the same level. Then every subtree is also an AVL tree. So like that, this is the condition where you go for this subtree, fine, or AVL tree, right? So then we go for the detailed explanation about this thing. Now when explained, we can say that if a binary search tree that is height balanced in nature, then we call it as the BBST. So height balance means that the difference between the left subtree height and the right subtree height, it should be either -1, 0 or 1. It cannot exceed that one. Okay, so it should be, you see, I'll show you one here. You can check it here, that I want going to show you. Yeah, you can see it here. So you can see then the balance factor, it should be -1, 0 and 1. Say for example, I take the example here. Say for example, you see this is Z and Y. It is not only the numericals, I can put the character also. So Y is less than Z, so it should be the left to of that root node. Then X is also less than Y, it should be left to that one, right? So this is called left skewed tree. So in this left skewed tree, then we go for the rotation, that is different thing. First of all, we see the balance factor. If you come to the X here, so here also nil, here also nil. That means left, what is the left side height? It is 0, minus right hand side it is 0. 0 minus 0, it is 0. So here the label is equal to 0. Okay, I can write and you can put it as 0. Coming here to y, here left hand side already having 1 and right hand side 0, then 1 minus 0 it is equal to 1. So 0 is okay and 1 is also okay. Okay, so if you want I can show you a demonstration also. Yeah, that it will be suitable for you. Yeah. Yeah, so we see it here. Yeah, yeah, so here you can see it is happening here. Left hand height it is 0, left hand height is equal to 0 and minus right hand side right hand height is equal to 0. So 0 minus 0 it is 0, right. Here at y it is 1 and here it is 0 because there is no leap here, that is 1 minus 0, here it is 1. But while coming to this one, so right hand side is 0, left hand side 1 and 2, so it is 2, left hand side is equal to 2 and right hand side is equal to 1, right hand side is 0, so 2 minus 0 it is equal to 2. Okay, so 2 is not there in this list, that means you see minus 1, 0 and 1 is allowed. It can be 0, no problem, it can be minus 1 or it can be plus 1, but here it is 2, so it is not balanced. Okay, so when you add this number z, it is not balanced. Similarly you got the right skew also, you will find here at this level, if you check it here, here it will be 0 minus 0 0, here this is 0 and this is 1, so 0 minus 1, this will be minus 1, and here left hand side is 0 minus right hand side 1 and this is 2, so 2 it is minus 2. Okay, so this is also not in the balance tree. Okay, so then both are, then they are not the AVL tree. You get it now? So when this balance of height is not there or balance factor is not matching to this one, then what you have to do? You have to go for some rotation. So that is the problem. So in the balance tree, in the AVL tree, we have to go for this thing, right? So next we come to our PPT. Then we see coming to this tree here, if you see the element, the key value is equal to 10 and 4 is less than that, I am putting to the left, and next is 14 is greater than 10, it is right. Then 11 is greater than 10, it should be right to this one, and less than 14 left to this one, and next is 19 is greater than 10, it should be right, then it is greater than 14, it should be right to this one. So at this level left hand side height is equal to 0 and right hand side, because there is no child node here. Here also left hand child, no left child, no right child, so it is equal to 0 0, it is 0. So this is 0 minus 0 0, this is 0. Coming here, left hand side one child, right hand side one child, so 1 minus 1 it is equal to 0. Okay, coming to this one here, the left hand side child, because here there is 0 and there is 0, 0 minus 0 is equal to 0 here, no problem. So here coming here to the root node, here left hand side you are having one child and right hand side we are having 1 2, you go this way, it is 1 2, it is also 1 2, so 1 minus 2 is minus 1. Okay, so 0 minus 1, so all these things are complying, so it is also, it is a AVL tree, we don't have any problems. Clear? Then notice that each node in the above BST contains two values. The left value denotes the height of the left subtree and the right value that denotes the height of the right subtree, what I was discussing to you, and their difference should be in the range minus 1, 0 and 1. So if it is violating this thing, then it will not be in AVL tree. Okay, this is the thing. Now a self balanced tree means that when you try to insert an element in the BST, whether you go for insert or delete, and if it violates the balancing factor, that means if it is not in that range minus 1, 0 and 1, then it dynamically rotates itself according to the make that self. Then what we have to do? We have to go for the rotations. So different type of rotations are that we will discuss now. So we can go for that, then so that it comply to that one. So when you complete that, it is the balance side is there minus 1, 0 and 1 in between, then we say that it is in the AVL tree, right? So this is the property we go for these things, right? Then we go for this, the pictorial representation of perfectly balanced AVL tree. You see, a perfectly balanced means you can see here the perfectly balanced. Here all the internal nodes are having 2 children, and also all the leaf nodes are at the same. Okay, this is called perfectly balanced AVL tree. And you see, to make it AVL tree, you see the difference, the balance factor here. It is left hand side 0 and minus right hand is 0. This is 0 0 0. So coming here, left hand side height is equal to 1. Here it is 1 1 minus 1 0. Here also same. Coming here, left hand side also 2, because you come explore this way or you explore this way, it is 1 2 2. Here also 2. So 2 minus 2 is equal to 0. So it is a balanced tree, and it is a perfect balanced tree because this is the internal things that are having 2 children, and all the leaf nodes are at the same level. It's clear. Now the same thing it is explained here. Height of left subtree. What is the height of left subtree? Height of the left subtree here it is 1. What is the height of the right subtree? This subtree and the, what is the height of left subtree here? It is 2. Height of the right subtree it is 2. 2 minus 2 is 0. Right. So in this way we can go for the. Now let us have the idea about what are the differentiation. What is the rotations? We go for that one. So let us we have. Check it whether it is by AVL tree or not. The left hand side you check it here. So here it is 14, and here left side the subtree it is height is equal to 0, and here also 0. So 0 minus 0 it is 0, no problem. Here coming here, because left hand side nothing is there means it is 0. Right hand side 1 is there. 0 minus 1 it is minus 1. Here it is 0 0, and here it is coming left hand side 1, right hand side 1 2. 1 minus 2 it is minus 1. So that means it is 0 and it is minus 1 and it is minus 1. So it is coming in that range. So it is a AVL tree. But what happen if you go for this one? If you go for this one, so 3 8 10 14, and you put another number 17. Suppose I add it there, what will happen is here it is 0 0, you can understand. Here it is 0 1 is minus 1. Here 0 0 0. 0 minus 2 it is minus 2, it is violation. So here left hand side it is 1 and right hand side 1 2 3. So 1 minus 3 is minus 2, it is also violation. Okay. So when these violations are there, then what you need to do? You have to go for the rotations. If you minutely observe this one, this 10 14 and 17, so these are called the right skewed. When you is right skewed, you have to go for the left rotation. Left rotation means 14 will go up, 10 will come to the left, and 17 come to the right. Okay, so this is the things you just rotate it. That means 14 will be up and 10 will be down. So it will be there. This is the thing. Okay, and after doing that one, we can see the same thing we did it here. We did it here. You got it now. So then this is there the AVL biometry. Okay, this is the thing. Okay, but let us go for another example. Right skewed. Right skewed means what? This 8, all the things are there. Okay, in this 8, 10, 14 and 17. So if you see the level, here it is 0 0 0. This is 0 minus 1 minus 1, 0 minus 2 minus 2, 0 minus 3 minus 3. So this is not this is right skewed, and it is not a AVL tree. Then what you have to do? In the right skewed, what you need to do? Right skewed, you have to go for the left rotation. Okay, so the same thing we are going. The height of the BST. So if you see the complexity, it is order of log n. So if you go for the AVL tree, all things it should be order of log n. Okay, so we have the different type of rotations here. As I explain you, we have 4 type of rotation. One is the left rotation, one is the right rotation, one is the left right rotation, one is the right left rotation. So what are they? Let us see. So now let us see. We go for the left rotation. So we see here it is a right skewed binary search tree. Okay, right skewed, because why? Because 14 is greater than 10. So I am putting to the right. So 17 is greater than 10 and greater than 14. So we are putting it to the right. And I go for checking the balance factor. Here there is no leap here, there is no leap here, there is no child. So 0 minus 0 it is 0. Then here left hand side here it is 0 and right hand side 1. 0 minus 1 is minus 1. So it is 0 minus 2 is minus 2. So this is a violation. When it is a violation, then what you need to do? We have to go for the automatic, it has to go for the rotation. And what type of rotation is suitable? We can go for the left rotation. We can go for the left rotation. In the left rotation, what you do? The 14 will go up and 10 will come down. You see here, the next page we can explain it here. So the same thing it is done here, and now 10 is come down, 14 is gone up, and 17 is there. And if you check it, the balance factor, here is left hand side is 0, right hand side 0 minus 0 0, here also 0 minus 0, here left hand side it is 1 and right hand side 1, so 1 minus 1 it is equal to also 0. So now it is a AVL tree. You got it now? So like that we can go for this thing. Then we go for the right rotation. Suppose we have a left skewed BST, that means I have the root node, it is 5, then another I am inserting 4, so 5 being less than 4, 4 being less than 5, so it will come to the left. Then I want to insert 3, so 3 being less than 4 and less than 5 means it will come to the left, then less than 4 means it will come to the left, right? So this is there. Now if I want to go check the balance factor, here as you understand it 0 0 0 minus 0 0, 1 minus 0 1, 2 minus 0 it is 2. So it is again a violation. So when it is a violation of this thing, your left screw, then we have to go for the right rotation. In the right rotation what we do? So that means the 5 will be pushed down and this 4 will come up. Okay, that means 4 3 5. Same thing I have done it here. So 4 3 5. So you check it here, it is a AVL tree. It's clear. Now we go for the left right rotation. The left right rotation, what is the thing that, suppose I have a root node and the key is 30, then I have to insert something that is 15. 15 is less than 30, so it will be to the left. Then I want to insert 18, so 18 is less than 30, come to the left. Then 18 is greater than 15, then go to the right. Okay, so now it is first left, then it is right, so it is called left right rotation. In this left right rotation what we do, we need to do first, we have to go for the changing of all the things. First of all, we have to go for the rotation. That means first there is a problem here. Okay, then we have to go for the just rotate it. In the rotation what we will do, 18 will come up and 15 will come down. 18 will come up and 15 will come down. So that, but then it cannot be in the right hand side because 15 is less than 18, so it will come to the left, right? So you see here, so then when I rotated this one, 18 has come up, but 15 being less than it has to come down here, but it cannot come here because 15 is less than 18, so that why it will come to the left hand side. It is just you apply your common sense and put it here. So if this is the case, then it will come to the left scoot. In the left scoot, that means you have to go for a right rotation. So initially I gone for the left rotation, then I have gone for the right rotation. Is clear? You get left means this one is just left, this one just going left, right? So it is making like this. Then I am to go with the right rotation. Right rotation, what you need to do? Push 30 come here, 18 up, 18 is here and here. So then it is a perfect and it is also a AVL tree. You get it now? So now another thing, we go for the right left rotation. Suppose initially I have the key 5, the root node key is 5, then I have to insert 10. 10 is greater than 5, then it will go to the right side. Then I want to put 7. 7 is greater than 5 but less than 10. So either first is right, then is left. So this is called right left rotation. In this right left rotation, then first of all we try to find what are the balance factor. Balance factor here, what we say here, it is 0 0, you understand, and here because left hand side 1, right hand side 0, so 1 minus 0 it is 1, and here left hand side 0, right hand side 1 2, so 0 minus 2 it is minus 2. So this is a violation. So in this violations what you need to do, so you see there is a very tricky thing you have to remember. So this one is coming left, then you have to rotate right, you have to rotate right. Okay, you have to rotate right means this 10 will come down and 7 will go up. Okay, when that means it will be 7 and it will be 10. Then applying this common sense, the 10 will be to the right of that one, so it has come to this one like this, right? So once it is coming that one, it is, you can see it is a right skewed. Okay, when it is a right skewed, then you have to go for the left rotation. The left rotation, what you do, push 5 down, so 5 will come down and 7 will go up. So this is the things it is done, right? So now by this time you have understood what are the various type of rotations that takes place here in the AVL tree. Okay, and this is the thing, it is automatically done in the AVL tree, we need not do it manually, right? So now let us go for some insertion. I want to insert something, you can go for some insertion, you can go for deletion. You remember one thing, so first you check it whether it is empty, the tree is empty or not. If tree is empty, then first element you insert, there is no problem or that one. Then you go for inserting the second element. Then before going inserting the second element, you have to check the key of the key value of the second element. It is less than that the root or it is greater than that one. If it is less than, it will come to the left. It is greater than, it will come to the right. Okay. So now the same thing I carry out and I go ahead with a number of things. Then second thing is that up to 2 you don't have any problem because 2, say suppose initial was 12 and I was insert 3. So 3 is less than 12, so I put the left. Here it is 0 0, here it is 1 0, I don't have any problem. But I want to insert something 9. So 9 is less than 12, it should come to the left. Then 9 is greater than, it should come to the right. So it has come here. Now what is the next thing I have to do? I have to check the balance factor. In the balance factor it is 0 0 0, it is 0 minus 1 minus 1, 2 minus 0, it is 2. So it is a violation. So if it is a violation, then what type of things you try to check it here? It is LR. It is LR. LR means you have to go for the left rotation. In the left rotation, what you do? 9 will come up and 3 will come down. Okay, so that it will become like this. Then it has a your left skewed. Okay, your left skewed. The left skewed, what you have to do? You have to go for the right rotation. In the right rotations, what we do? So this 9 will go up, 12 will come down. You can see this is the thing. It is coming to like this. Now it is there. Now suppose I want to insert another element that because you see first was 12, next one is 3, and 9 is already over. Next I want to insert 4. If you want to insert 4, so 4 is less than 9, it will come to the left. Then 4 is greater than 3, that means it will come to the right. So I put it here. So while I am putting it here, so here you don't have any problem. Here 0 minus 1, it is equal to minus 1. Here 0 0, okay. But here coming here, because 1 to 2 keys are there and there, and here height is 2, this and this, and here it is only 1. So 2 minus 1. So I don't have any problem here. I don't have any problem because 2 minus 1, it is 1, 0, it is there, it is fine, it is in the range. Now suppose I want to add another, that is, see, after this I want to add 6. If you want to 6, so 6 is less than 9, so it will come to the left, and 6 is greater than 3, it will come to the right, and 6 is greater than 4, it will come to the right. So here it is 0, here 0 minus 1, it is minus 1, here 0 minus 2, it is a violation, here 3, and here is 0, 3 minus 1, it is also 2, it is a violation. Okay. So in this case, what you have to do? Now let us take one by one. First I go for this one. If I go for this one, it is already a left skewed. It is a right skewed. The right skewed, what you have to do? You have to go for left rotation. That means 3 will come down, 4 will go up, and 6 something. 4 is up, 3 is 6, it is there. Now checking it there, here it is 0 0, here also 0, here 1 1 0 0, here is 2 minus 1 1. So it is perfect, we don't have any problem. Then I need to add 2. When you add 2, so 2 is less than 9, it will come to the left, and 2 is less than 4, it will come to the left, and 2 is less than 3, it will come to the left. So it is there, now it is there. Now when it is there, then you check the balance factor. Here it is 0 0, here it is 1 0, 2 1 0, but 3 1 it is 0. That means here there is a violation. Here there is a violation. So violation where? The violation is there at the top. Okay. So if there is a violation there, then what you to do? Then you have to go for the right rotation of that one, right? In the right rotation, what you do? 0 0, here 1 0, 2 1 1, it is okay. Okay. Then what we do? If you make the right rotation, 4 will go up. 4 will go up. If 4 is going up, then what is the next number? 9. So 9 is greater than 4, so 9 will come here. Okay. Then he is telling 12. So 12 is greater than, so it is coming here. But you see, 6 was attached to 4. 6 is a child of 4. Then when you put that one, now you check it. 6 is greater than 4, so it will come to the right. 6 is less than 9, it will come to the left. It is there. Then 3 2, it will be there as it is. Now you check, it is a AVL tree. We don't have any problem. So like this you can go for the insertion, also the deletion also you can do in the similar manner, right? Then what are the key points? So AVL tree with n number of nodes, suppose number of nodes is equal to n, then we can have the maximum height, that is log of n base 2, right? That is the floor value. Floor value, you know about the ceiling value and floor value. Suppose we got some n is equal to 5. So n by 2, suppose something. So 5 by 2, it is coming 2.5. 2.5 you take the floor value, it will be 2. But you take the ceiling value, it will be 3. That is the ceiling means just next, floor value means just below that one, previous one, right? And the height of the AVL tree with n number of nodes cannot exceed 1.44 log n base 2. That is also you have to remember. Then maximum number of nodes can be. So these are the things, all the things we check it there, we don't have any problem. So you get some gate questions, we are preparing for the gate questions. These key points are very important for them. So we will be solving some gate questions in our coming videos. So there I will tell you how to solve this type of problem. Then coming to the conclusion, we learned that AVL tree and why we need it first. Then we learned the different type of rotations and they are possible in AVL tree. Then followed by the rotations, we also did insertion in the example tree. Lastly, we talked differently the key points that should remember with AVL. So thank you for watching this video. If you really like this video, please do share with your friends, and my sincere request you, please do subscribe. Don't forget to subscribe, because so many videos I'm making. Once I see the number of subscription, I'll be first of all encouraged. Second thing is that what are the new videos all the time, it is not possible to send to you all, so you can automatically get link to that one. Okay, once again, thank you and take care of health. Bye bye.